a una edición más del Seminario Phd, nada más y nada menos clarísima. Y bueno, que mejor ocasión que el décimo ponente sea una persona 10, como nuestro querido compañero y veterano Manu. Y nada, well, today's talk will be in English. Well, Manu wants to do it in English since there are some people in the audience who are not fluent, or it's not his native language. So it will be in English, and well, he will be talking about persistent homology, mathematics and science, and as it's customary, we will begin with the introductory video.
Okay, thank you very much, Carlos. So I will talk, as he said, about persistent homology, and as you can see the title, I will explain its place in mathematics and how it relates with other science. Can you hear me properly at the background? Okay, good. So what about online? Is it fine online? Okay, nice. So this is the idea. I will go slowly, so if you have any doubt, you can ask me anything during the talk. I don't know. So, just 1 second. Oh. Okay, sorry about that. So, what is persistent homology? That's the question I want to ask. I think that some of you were in the morning doing this seminar, and you might have seen this word during the seminar. He showed a lot of papers, but he didn't explain what it was. So, because it's a very hot topic now, so that's why it appears so much. The idea of persistent homology is to study how holes evolves depending on a parameter. With holes, I mean a different concept depending on the dimension. It can be the connected components, it can be cycle, it can be cavities, depends on the dimension, as I said. So the good point of persistent homology, and that's also an explanation of how it has become so popular, is that it has a very good intuitive meaning. So you can intuitively understand it. So here is a video where you can see what I mean. Just 1 second. Yes. So as you will see, we will have one parameter, in this case, the radius of a ball, and we will create a geometrical entity, and when cycles appear, you write it down in what is called a barcode. So I will put it again. We make some balls increase, and when two balls touch each other, you put an edge connecting the vertices. Whoops. Sorry. Yes. When two balls connect, you put an edge. When three balls connect, you put a two-dimensional simplex, a triangle, a field triangle, and so on. As you can see, here there were two holes. I don't know if you saw them. I wrote 2 bars, and now one hole will appear here. So there's one hole here, one cycle, and I write down here this one cycle. Okay? I keep the track of it until it disappears. I don't know. Yes. Okay, so there were two concepts that appeared in that video. One was a simplicial complex, which many of you might be familiar with it. It's like a generalization of graph. You can see it like that, where you have vertices, you have edge, and you have triangles, you have tetrahedron, you have other figures in several dimensions. The only requirement is that you glue them in a right way. So you have edge, you have to glue vertices with them. If you have triangles, you have to fill edge, and so on. But the geometrical idea is just that. And the other concept which appeared in the video was the concept of a barcode, which is just you keep the tracking of the cycles in this case, or you can keep the tracking of the connected components, and so on. Any doubts so far? Okay. So, but what's the mathematics behind that? That's the first thing I want to tell you in this talk. The mathematics behind that is constructed on the notion of homology. So what's homology? Homology, I think if you want, it's kind of difficult to explain, but we have an intuitive notion of holes. So it's enough to know that it's a process that assigned to these geometrical entities, which might be a simplicial complex, but it can also be a topological space, a manifold, can be any kind of geometrical entity. You assign to it a vector space in such a way that the dimension of that vector space coincides with the number of holes of the intuitive idea of holes you have. Okay, so in this case, we are assigning to the simplicial complex a two-dimensional vector space. Why? Because there are two cycles there. Okay, is it clear? Okay, so how does this relate with persistence and the concept of barcode? So there is another cool thing about homology, and it's that it does not only give you a vector space, but also linear maps. So you have a sequence of simplicial complexes, and you know the relation between them, then you not only have these vector spaces, but also the linear maps between that vector spaces. Okay, so you will have, if this is the zero-dimensional vector space, you will have this 0 here. And if you have here one hole, you can send it with a linear map to that hole here. So you are assigning this one-dimensional vector space to a one-dimensional vector space here, each of them meaning the concept of hole somehow. So thanks to these linear maps, you can keep the track of the classes of the vectors, and that's how you can construct these barcodes. So here in this small example, I don't know if you can see it from there, but there is a hole first, which is born first. So at this moment, you only have one hole, and then another hole appears. So you have two holes here. So then you have two bars, and then the two holes disappear. So the two bars disappear as well. Yeah? Does it make sense? Cool. So what's the algebra behind this? And why do we know, for example, that if we always, so how do we know this barcode construction does not depend on basis, for example? How do we know it will always exist? So there is some mathematics behind this, and it's the following. If you want to think about it algebraically, you try to forget the geometrical structure we saw before, and you keep the vector spaces. And there are many ways of formalizing this, but I think one of the most intuitive ones is as a quiver representation. So you have this sequence of vector spaces, and somehow you can see it as the representation of a quiver, as I said, which is some kind of graph. You have this graph on the top, which is just a sequence of points and arrows, right? And you assign to each of these points as a vector space, and to each of these arrows, a linear map, okay? This is what's called a representation. You might have seen maybe representation of groups, representation of graphs, I don't know. This is a representation of a quiver, the same concept, but on a different figure, okay? Then all this algebraic structure is called, we can call it M, for example, and we can play with it. And it has been studied since long time ago, and basically a nice result you can see is that this quiver representation the representation of this type of quiver we saw before, there is a nice decomposition theorem, which tells you that this algebraic M I told you before can be expressed as the sum of it can be expressed uniquely as the sum of these M's. Okay, so you have a decomposition. So how does this relate with the barcode we saw before? So actually, the bars we saw are this decomposition. These bars are some kind of very specific type of modules, very specific type of representations, which has this form of a bar. So you can actually prove there's a unique way of calculating these bars. Yeah. I know it's a bit abstract, but if you are curious about this, you can ask me later and we can see in details how it works. So what I wanted to say is that even if it had this intuitive meaning, it has actually motivated some mathematical results. So this decomposition theorem originated like 40 years ago, and it's well known since then. But thanks to the interest in persistent homology, some new results have become. So for example, there is the first constructive proof of this result, which does not only give you the existence of the decomposition, but also gives you a way of calculating it. Was done like only 10 years ago. And there have been also, for example, decomposition theorems, which deals with, instead of discrete quivers, deals when, for example, you have a continuum here. So you define the persistent homology in a continuum setting instead of a sequence, and results like that. So that's kind of the relation with theory of representation theory. I think it will be better, since I'm in the middle of the talk, to change now to topological data analysis, okay, which is kind of the applied branch of this field. It's a way of just applying topology to data, basically, to understanding data. There are many ways of attacking this problem. For you who went to the talks during these days in the mornings, you might have seen another ways of applying topology. For example, this connected component algorithm where he saw when clouds merge somehow. So in this case, the approach we follow is similar, but a bit different. Sorry. So in this case, the workflow will be the following. We'll start with some kind of data, which can be anything like time series, images, point clouds. And from it, we define a filtration of complexes. So a sequence of simplicial complexes, like we saw before. There are many ways of defining this. We saw one with these balls, increasing the radius and connecting, but there is completely freedom to define this. So that's kind of the art part of data analysis. You have to think about what's the information you want to encode and how it can be summarized geometrically somehow, and define that way of creating the simplicial complex. Once you have the simplicial complex, you calculate the barcodes using persistent homology, which will be this here. And that's nice because it's quite intuitive. You have an idea of what's going on, but the problem is that it's not a vector, and it's a pretty bad space for applying statistics or applying machine learning and things like that. So you cannot study well these spaces. So what's usually done is a last step where you vectorize somehow this. So you send it to a vector space and you study it there. That's kind of the typical workflow we follow. So here I have a small example of application when we apply it to cell tissues. Okay, so this is epithelial tissues, which is a kind of tissue which forms organs in animals. And it has an important role in development of organs, yes. So it is believed that they follow concrete patterns and a concrete organization, somehow the cells, and that if you don't follow that kind of organization, it might be a way of detecting malfunction or illness in organs before they are complete form. So it's interesting to study the geometry of these cells. The way of studying these tissues is to look for models which somehow keeps the information you want to summarize in the model. So for example, you can try to imitate the contact network of the cells, which will be a topological property. So you try that the connection of the cells is similar in the model than in the natural tissue. Or you can try to study the relative position of the cells, so how cells are placed in the image. That's the things you try to imitate with the model. So biologists, I'm going to study the first one in this case, how you can study the contact network. And the idea is the following. These two things are quite qualitative in nature, but you want numbers so you can apply statistics. That's the same idea we told before. So how can you somehow summarize these things which are qualitative in numbers? But not in any way, but in a way you have guarantees your numbers actually measure what you want. That's the idea behind this, and what biologists were asking us to do. The traditional way of doing it is just counting the number of neighbors of each cell. So you pick one cell, you count it has 6 neighbors, you do it for all the cells and make an histogram. So this will be like the amount of cells which have 4 neighbors, this is the amount of cells which have 5 neighbors, this is the amount of cells which have 6 neighbors, and so on. And then you compare the histograms and see if they are the same. The question is, okay, so they have the same number of neighbors, but does this mean they have the same contact network? Can a more sophisticated method find new differences that we're not seeing from the old methods? That's a question we want to answer. So I think I'm skipping the normalization part. And let's see how we construct the filtration. So the idea is the following. Since we want to keep this contact network somehow, what we do is we assign to each cell the number of neighbors it has. Okay, so in this case, all these cells has 6 neighbors, and this cell has 7, because there is a division there. So this cell has 7. And then we put an edge from each of these cells if they are touching each other. And we put also a weight on this edge. And the weight is the maximum between the weights of the 2 cells which are in the edge. So in this case, it will be 6 because it has 2 6 on both sides. And in this case, it will be a 7 because we have a 7 and a 6. So we pick the maximum, which is a 7. Okay, this will place an order in the cells and an order in the edges. So cells with lower number will appear first, and then cells with greater number will appear after. And the edge will appear when the second cell appears. Okay? So here we have a visual example of how it works. We start with 0, 1, no cells. Then, I don't know if you can see it, but some cells appear in the boundary first. They start appearing in the boundary because we pick like a boundary, and this cell has less neighbors. And then here we have 4 cells, which there are already a bunch. And now cycles start appearing, connect components start merging, and then barely all are together, and finally all merging one. Okay. And this information is again summarized in a barcode. The red bars are the connected components, and the blue bars are the cycles. Okay. And then we need numbers. So we need to somehow calculate numbers from this barcode so I can apply statistics. Yes, I'm not telling how we calculate these numbers, but if you are curious, you can ask later as well. And the results are the following. So the statistical test said that we could not find differences between the contact network and between the contact network of the natural cells and the contact network of the models, okay, which was the first idea. However, we could find differences between the larva tissues and the prepupa tissues, okay, which was something interesting because it's kind of difficult to find differences between these 2 stages of development. However, when we look at the results more carefully, we found that the differences were directly explained by the difference of 4 and size. Was directly explained by the number of cells with 4 neighbors or 6 neighbors. So we realized we were measuring something, but it was actually something which was known from before. So the experiment at the end of the day, what did was supporting the idea that counting the number of neighbors is actually accurate. If you can complicate the model, you can do different things, but we didn't measure anything different. So I also had some positive results in with other tactics, but I think it was cool to see this, especially because there are many people starting the PhD, and I think it's cool to know that you try things, you have good ideas, you spend a lot of time on them, and then at the end of the day, you kind of did nothing. That something's happening. But it's cool to know if you learn something in the process and you keep working on it, at least you learn and you can do it better the next time. That's something which happens all the time. I have here some references. I think I'm already in 20 minutes. I have 1 minute, so to tell you a bit more about our research, just in 1 minute. If you are wondering what else have we done, we have also keep on with the cells, which was we did more experiment with this. Our research has also consisted on in this workflow here. We have also studied this transfer vectorization, so we can give guarantees of how this vector will actually measure what we want, especially a method which is called persistent entropy, which is it's being used a lot during the last year, so we are quite happy with it. And the other research we have been conducting is also related with this decomposition theory, because for this kind of situations where you do not have only one row, but you have two rows, which happens when you want to study how, for example, one point cloud can go inside another point cloud. In this situation, you don't have a decomposition theorem. I mean, you have one, but you know you can never calculate it. So we have also studied what we can do in this situation, how we can attack algebraically these problems and what things can be calculated. And that was everything I wanted to say. Here are some references at the end. Yeah. Thank you very much.
I was just wondering if you can get a little bit more into the number, into the vectorization you could explain.
Yeah, sure.
Because I think the great part from studying this kind of data is critical to obtain a good vector space.
Yes. So, for example, yes, here I have this small example. This persistent entropy, which is basically, do you know Shannon entropy? Probably you are familiar with it. Shannon entropy. So it's basically Shannon entropy, but instead of probabilities, you pick the length of the bars, and you divide by the total sum of the length. So it's like a probability space because everything sum up to 1. And so this was defined from before, and we look for its property. So for example, one trivial property that you might look is that if you only look at the length of the bars, you forget about when the bars are born or die. You forget in which moment of the parameter it appears. You only care about the length. So that's, for example, a trivial kind of property you might realize. So that kind of property is the one we study, but more complex one. The aim of this is not answering machine learning question, but to use them as a vector. So for example, if I were doing a machine learning task instead of a number, I could, for example, make advantage of that parameter I have, because I have a parameter, and then for each moment in time, calculating, for example, this number, but only with the bars which are alive at that place. So instead of summing up everything, I just sum the bars which are alive in that place. So that creates me a function which has more information and which can be actually used as a machine learning input, which will be the aim. There are also like theoretical, you can also apply this theory to study machine learning tools, but that's another field I haven't used.
I have a question online. Víctor te pregunta una tontería teórica que alguna vez me has comentado. ¿Qué restricciones hay sobre los quivers para poder considerar barcodes o análogos sobre ellos? Es decir, ¿qué tipo de quivers se sabe que tienen teorema de descomposición de los ejemplares superiores?
Okay, so Victor asked. So Victor asked online. Yes, Victor asked online if what kind of restriction. So sorry, as I said before, you could see this quiver representation as some kind of graph which has a vector space assigned somehow. Okay, so he asked, okay, so you have a representation for this kind of graphs. For what other kind of graphs you have a representation? So actually, 2 years ago, it was proved, Victor, that you have a decomposition for all small categories. So if you have a small category, you have a decomposition. The problem is that you cannot calculate it. So you know it exists, but when you have even a very simple small category like this one, if there were here 6 points instead of 5, so it's like a ladder, right? It's a set of squares. If you have 6 points in each of the rows, then you know it exists, but you know that it's a wild set, and there is no way of calculating them or using them for actually represent discrete data. So yes, that's the answer. We already know that decomposition exists for all small categories, but we also know that we cannot calculate it in most of the cases. I don't know if.
Dice que muy bien, aunque muy guay, aunque no puedas calcularla, que te pedirá la respuesta.
Okay. So. About what, sorry? Maybe, oh yes, sorry, I put it in the abstract, didn't have time to it, but yes, I was doing 2 things. One is a result. I don't know, do we have? Yes. So I don't know if you hear it online, but I have been asked, so how does it relate with metric spaces? So the idea is the following. When you have 2 metric spaces, X and Y, I don't know if you can see it online. Okay. So if you're online, you can click on, I'm saying hello in the right left of the screen. You can click there and watch me bigger. So if you have 2 metric spaces, which can be, I don't know, some kind of manifolds with like Riemannian manifolds or discrete point set, then if they live in the same space, you can compare them using the Hausdorff distance, right? You can use the Hausdorff distance. We see it in the bachelor, which is just to compare point per point and pick the best approach somehow. But when they live in different spaces, this gets complicated with a concept which is known as Gromov-Hausdorff distance, which is the following. You pick these spaces and send them to a common space by isometries. So you don't change their geometry, send them to a common space. And calculate the Hausdorff distance in this common space. So the infimum of all these distances is what's called the Gromov-Hausdorff distance. Intuitively, it has a very concrete meaning. I like it with point sets. So the idea is that if you have 2 point sets, in order to compare them, you can move them in a rigid way. So you can translate them, rotate them, and see if they fit somehow. What's the best position they fit. But you cannot change the geometry of this point. So you move them close, and you see the Hausdorff distance. You see what's the Hausdorff distance with these movements, but you cannot do anything else. Is it clear what's the Gromov-Hausdorff meaning somehow? Okay, so the problem of this distance is that it's very difficult to calculate. So one result which was quite cool from persistent homology is that you can compare barcodes with a distance which is easy to calculate, which is called the bottleneck distance. So one result is that the bottleneck distance in these spaces is always smaller than the Gromov-Hausdorff distance. And that's pretty interesting because it's really difficult to find lower bounds for this distance, which actually works well. So these are the kind of results we have. And another kind of results is that this construction you saw here, you can do it for infinite number of points. So instead of a sample, you can have actually a circle with infinity points, and then you, yes, people who study metric spaces use Rip's complexes to study that spaces as well. So there is also a connection with that theories, but that's another talk. Okay, that's what it is. Sure. Yes.
I'm not quite sure if I have understood. So you mean you want to compare sets of two different metric spaces, and then you embed these two metric spaces into a larger one.
Yes.
And then you define some metric there.
No, kind of. I mean, the idea is you can embed them in a common space. You don't know which one, and then calculate the distance here, right? So the distance, so the Gromov-Hausdorff distance, what it does is that you vary zeta. So you vary this embedding space and take the minimum of all zetas. So you look for all distances you can calculate with zetas, which one is the minimum. That's the distance you get, kind of. I don't know if it's clear now.
Well, much clearer, thank you.
Okay, sorry.
Can you do this for any metric space to make them to be, for example, complete? Or...
I don't know because I have never directly worked with it. So complete was that if they converge, you have a sequence of points, they converge.
Finite, you cannot escape from the space with finite.
I don't know. I don't want to. Yeah, the sequence of. I don't want to. I think so, but I don't. I'm not sure because I didn't push it to the weird cases. I just kept with manifolds and point clouds. So I don't really know. Sorry. You mean? You mean Hausdorff?
Yes.
It could be anything. It could be a point cloud. It could be a manifold. I don't know if.
No, I think but when you say that X is a metric space, I suppose that X has symmetric itself.
Yes. Sorry. This Riemannian manifold, which is a metric, and this finite point cloud is a finite metric space. What I mean. Sorry about that.
Okay. So we have no more questions.